Today, we're going to peek under the hood of the digital economy. We're going to explore the incredibly complex, high-stakes system that powers every single online purchase you make. This isn't just about moving money around. It's really about the architecture of digital trust itself. You know the feeling, right? You find that thing you want, you pop in your details, you click that button, and poof, a success message appears. But between that one little click and the confirmation, there's this silent, high-speed ballet of technology that kicks off. Today, we're going to follow that journey, step by step. Now, what's really wild is the level of expectation here. This number, 99.99%, or 4 nines as engineers call it, is the target for uptime. Think about what that means. It means the entire system can only be down for about 52 minutes for the entire year. For a machine that's handling millions of transactions, anything less than near perfection is, well, it's a catastrophe. The stakes are just unbelievably high. And when we say the stakes are massive, we are not kidding. These systems are processing millions of transactions every single day, with huge bursts of thousands per second during peak times like Black Friday. In this world, a fraction of a second of delay, or one tiny little error, can cost millions of dollars and, maybe worse, completely shatter customer trust. Okay, so let's start that journey. You've just clicked buy. Your browser fires off a request, and it's packed with all your payment details. But before that request goes anywhere near a bank, it has to pass a whole series of crucial internal checks. These are all designed for security and, just as importantly, for safety. The very first thing that happens is a process called tokenization. Your credit card number is immediately swapped out for a secure, random token. From this point on, the system almost never touches your raw card details again. This shows off a core security principle that's just brilliant in its simplicity. You can't leak what you don't have. It's a simple idea, but it dramatically reduces risk and the huge burden of compliance standards like PCI-DSS. All right, here's another key concept. It's a big word, but a simple idea. Idempotency. Imagine your internet connection's a little spotty, and you get impatient and you hit buy twice. How does the system know not to charge you twice? Well, it uses something called an idempotency key, which is kind of like a unique ticket for your specific purchase. The system acts like a bouncer with a perfect memory. It sees you've already used that ticket, so it doesn't let you in again. It just shows you the result of the first time you tried, preventing a nasty duplicate charge. So before it even thinks about contacting a bank, the system runs this internal gauntlet. First, it validates the whole request and checks that idempotency key we just talked about. Second, it gets a real-time risk score to check for fraud. Third, it creates a temporary log of the attempt. And finally, and this is so important, it places a temporary hold on the funds in its own internal ledger. Only after clearing these 4 hurdles is it ready for the main event. And now we enter the authorization maze. This is the real-time part of the whole process. It is an absolute race against the clock, navigating this complex web of external networks, all to get a simple yes or no back from your bank. And that clock is ticking, fast. The target is to get that response from the card issuer, the bank that actually gave you your credit card, in less than half a second. Any longer than that, and you, the customer, you start to get antsy. You start to wonder, hey, did it work? Should I click it again? This is the critical path that determines whether the whole experience feels instant or just frustratingly slow. So how does it do this so fast? Well, it's through this brilliant piece of architecture called the connector layer. The best way to think of it is as a universal translator and an incredibly smart traffic cop all rolled into one. It knows how to speak the language of dozens of different banks and processors. It can intelligently route your payment request down the cheapest path or the most reliable path. And if that path is suddenly blocked, it instantly reroutes to a backup. This little layer is what ensures both incredible speed and rock-solid resilience. But while all this high-speed communication is happening, there's one component that sits silently right at the heart of the system. It acts as its memory and its conscience, the unforgettable ledger. And this is, without any exaggeration, the most critical part of the entire design. This is its whole job description. When there's a dispute, a question, or an audit, everyone turns to the ledger. It literally does not matter what any other part of the system thinks happened. The only thing that matters is what the ledger says happened. It is the absolute, unimpeachable record, period. Its power really comes from a few core principles. For one, it's immutable. You can add new entries, but you can never, ever change the past. This creates a perfect audit trail. It's also built on database principles known as ACID, which is basically a set of guarantees that ensures every transaction is processed reliably and consistently. It's the ultimate guardian against financial chaos. Okay, so the system gets that yes from the bank. You see the success page. For you, the customer, the transaction is totally over. But for the payment system, oh, the work is just getting started. What happened so far was just an authorization. So, this is a really crucial point to understand. An authorization is just your bank saying, yep, this person has the funds, and we've put a temporary hold on them for you. But the money hasn't actually moved anywhere yet. The capture is a completely separate later instruction from the merchant to say, okay, now actually go and take the money. This kicks off a whole new, much slower timeline of events. Later on, often at the end of the day, all those capture transactions are bundled together in a process called settlement. A day or more after that, the payout happens, which is when the money finally arrives in the merchant's bank account. And all the while, running constantly in the background, is reconciliation, this super meticulous process of checking the ledger against the bank statements to make sure every single penny is accounted for. So let's zoom back out for a second. What have we really been talking about here? All these different components, the tokenization, the ledger, the connectors, they aren't just for moving money. They're all for building and maintaining digital trust at a massive, massive scale. And this trust, it really rests on three fundamental pillars. You've got reliability, that 4 nines of availability we talked about. You've got security, using methods like tokenization to protect our sensitive data. And you've got scalability, which is the ability to handle Super Bowl-level traffic every single day without even breaking a sweat. You absolutely need all three to succeed. Now, here's what's really interesting. Building a system like this is all about making a series of critical trade-offs. Let's just take tokenization, for example. Do you build your own secure vault in-house? Well, that gives you way more control, but it is a massive operational and compliance headache. Or do you use a trusted third party? That's way faster and easier, but now you're dependent on another company. There really are no easy answers. So that's a quick look inside the architecture of a modern payment system. It is a true marvel of engineering, designed from the ground up for security, for scale, and for near-perfect reliability. And it leaves us with a really fascinating question. As our whole concept of money becomes less and less physical and more just lines of code, what's going to be the next great challenge? What's the next frontier for building the systems that allow all of us to trust it?